Good morning. The class will start on 10:30 a.m. Thanks, Shuchira. Now, is it audible? Now, is it audible? Okay, thank you, Shomik. Let's wait until it's 10:30. Then I'll start my lecture. Yes, Madhushri, we have class from 10:30. So I'm gonna wait for 3 more minutes, then I'll start. I hope I'm audible clearly to all of you and visible also. Please let me know in the chat box. Okay, hello. Now, am I audible clearly? Madhushri, Shomik. Okay. Okay, thank you. I think the live is this is a live stream. That's why when I'm talking, your chats are popping up in front of my eyes. But when I'm talking, the my voice is going a bit late. So don't worry about the audio. I hope it will be managed somehow. If I'm not audible, then please let me know in the chat box. And it's 10:28. 2 more minutes we have to wait. Then we'll start. Okay, I hope everybody has spent their puja holidays nicely. I hope all of you are well. Shubho Bijoya to everyone. সবাই ভালো থেকো and পরেও এনজয় করো বাট সামনে পরীক্ষা আছে সেটা একটু ভালো করে দিতে হবে তার জন্য আমাদের একটু তাড়াতাড়ি করে পড়াটা শেষ করতে হবে দ্যাটস ওয়াই দিস ইজ আ লাইভ ক্লাস Okay, chats are also a bit late. Okay, it's okay. I think we can do with that, right? Because if you are listening to me, I'll wait for a while for your response, and you'll also wait for my response a bit. Okay. Actually, this is a live stream. That's why maybe there's a problem. Otherwise, I haven't recorded, and this is my first YouTube live. You already know that because I have taken the classes in the Google Meet. So this is my first live. I hope you'll pardon me if there is any mistake. Okay. Okay, fine. It's 10:30 in my clock. I hope everybody is here. So first of all, today we are going to learn about graph. Graph is a non-linear data structure. Already we have studied about several linear data structures like array, stack, queue, linked lists. So graph is one of the non-linear data structures, and when we are using graph, we have to set a definition first, like like there should be a set of vertices and there should be a set of edges. Okay, and they are interconnected with each other. So the set of vertices will be denoted by V of G. The graph is itself denoted by G of VE. V for vertices and E for edges. And V of G is the set of vertices and E of G is the set of edges. So this is a basic definition of a graph. I can use a picture so that you can understand it properly, and it will make you help understand how the graph looks like and what it contains. See, in this picture there is a graph G of VE, which is containing graph G, which is containing vertices V, edges E, with 5 vertices. It has 5 vertices. These are the vertices. These are the vertices. And these are the edges. The connecting path between any two vertices are called the edges. So we have here only 5 vertices and the connecting paths are there So they are called edges. How many edges are there? There are actually 3, 4, 5, 6 edges. 6 edges are there and 5 vertices are there. And this is also an undirected graph. Now, why this is written undirected? See, undirected graph means there is no direction from one way to another. Suppose I am going to go to from Kolkata, suppose Shialda to Newtown. There is a route. Suppose there is a one way road. We are assuming that one way road, that only one way we can go from Shialda to Newton. We cannot come back with the same road. We have to take another road to come back from Newtown to Shialda. That will be a proper direction. And for this case, there is no direction over here. If there is no direction, that is called undirected graph. That means if we are traversing from A to B with a path, then we can also traverse from B to A with the same path. So we are using one path for any two vertices to traverse. That's why this is called undirected path. There's no direction. And in case of directed path, yeah, 6 edge, Madhusri, right. So in case of directed path, it's you know uh, it is supposed to be like this, like this. See here, what we are doing is, if we go from A to B with this path, we cannot use this path to traverse from B to A, because there is a proper direction. We have to traverse like this. If we want to go from B to A, we have to go to B to D to then A. So we have to do this because there is no directly assigned path between B to A, but there is a path between A to B, but we cannot use that because the path is directed, already directed path. Okay, so that is the main point over here, directed and undirected. And here are the definition. A graph can be directed or undirected. Undirected graph, see the definitions you can read on your own self. I'm just explaining you. In case of undirected path, undirected graph, what we can do, we can use the same path between two vertices to traverse from both ends, right? And for directed graph, we cannot do the same. We cannot use the same path if it is not bidirected. This path is not bidirected. This is only going from A to B. We have to only go to A to B. We cannot go from B to A, right? Similarly, we can go B to C. Here is a direction, but we cannot come C to B. Okay? So I hope it's clear. If it's not, then please let me know in the chat box. I'll repeat. Definitely I'll repeat. Maybe it will be late, but I'll repeat. Okay. Next, there are some terminologies. Terminologies of graph. What are they? The graph terminologies are like there are paths. Any, path. What are paths? Basically, if we take an example, let's take this example. Any two edges, between any two edges, if there is a between any two vertices, if there is an edge, that is only called a path. Even if we traverse from any one vertices to 3 or 4 vertices, that is also called a path. Suppose we are traversing from A to C. How can we do it from A to B, then B to C. So this is also a path. Okay, is it clear? Any kind of traversing from any vertex to another vertex, let it be one vertex or two vertex or three vertex, doesn't matter. Any kind of traversing in the graph, like if we traverse A to E, suppose we are traversing from A to B, B to D, D to E, this is also a path. A, B, D, E, that is also a path. Suppose we are traversing from Kolkata, Shialda to Newtown, Newtown to Howrah, Howrah to Shialda, that is also a path. Okay. What is a closed path? Next one is closed path. Next one is closed path. In the name, the meaning is hidden. Already I have told you many times to follow the names to grab the definition. See, if we are considering a closed path, the initial vertex will be, yeah, what Madhushri? There can be more than one path for two vertex travel, right? Of course, more than one. How many paths if you want, depending on the graph, if you can have more than one, two, three, any time of paths, you can have it. Okay, you can have any kind of graphs, any kind of paths. More than one paths will be exist if there are more than one edges between any two vertices, any two set of vertices. If there are more than one edges are existing, then we can have more than one path. Okay. Next is closed path. See, closed paths mean the initial vertex will be the ending vertex. Initial vertex is, suppose we are, considering this graph. If we are considering A, B, D, A, this is a closed path. This is a closed path, A, B, D, A. So, A, B, D, A is a closed path because the initial vertex where we have started, that is the end vertex. Okay. And if we are considering about cycle, if this is a closed path is considered as cycle also, this is a cycle also. If the initial vertex or edge is repeating, suppose I am telling you like this: A, B, C, E, D, A, B. This is a cycle. A, B, C, E, D, A, B. This is a cycle. The edge is repeating, edge is getting repeated. The vertex A and B is getting repeated twice. So this is a cycle. And this is also a closed path. Okay. So closed path and cycle are quite similar. Okay. You have to remember this to, pursue further studies on graph. One is cycle and second one is closed path. These both of them are quite similar. Vertex and edges will be repeated in both in case of cycle or closed path. Okay. Okay. One thing, connected graph. Next is connected graph and weighted graph. See, any graph which is connected, they don't have any secluded vertex. Suppose in this graph, okay. In cycle, see what happens. In closed path, we can have a repeating edge like A, B, D, A, B. This is a closed path. And in cycle, A, B, D, A, repeated vertex. There won't be any repeated edges. That is the main difference. Repeated vertex are allowed in both cycle and closed path, and repeated edges are allowed in only closed path, not in cycle. Clear? I hope it's clear. Okay, let's move on to the next thing, that is weighted graph and connected graph. First of all, if there is no secluded vertex in any graph, like in this graph, suppose let's say in this graph, there's no vertex which is totally secluded from all of the other vertices, which is not connected with any edge. So that is a connected graph. This is a connected graph. That means any vertex is not connected, which is in the graph but is not connected. Suppose here is any vertex, suppose F, which is not connected but that is in the graph. But there is no edge by which we can traverse to that, vertex. So that's why we can call that a connected graph. I hope it's clear. So the next one is weighted graph. Let's see one example. So it will be easier to, understand weighted graphs. Just wait. See this one. This one is a weighted graph. This one is a weighted graph. Every edge is assigned a particular weight. Suppose, okay, there can be more than one repeated edge in a cycle. Repeated edge is not allowed in cycle. Closed path it is allowed, but repeated vertex are allowed in cycle, but repeated edge is allowed only in closed path. ABD is a cycle. If ABD, this is a closed path. You are traversing it twice. Nothing is changing. But this is not a cycle. We cannot consider it as a cycle. Okay? Okay. Let's move on to the next one. Weighted graph. Weighted graph is assigning a particular weight to every edge. Like what? If we are considering, we are traversing from Kolkata to Shialda to Newtown. If we are traversing, there should be a particular cost we have, bus fare or taxi fare or Uber, Ola, whatever. So there should be a particular cost. So that is the weight of that path, kind of like this. Try to think like the cost of that path. If we are traversing from, Howrah to Shialda, there would be a cost which will take to traverse that path. So that is known as, the weight of that path. Similarly, in graph, if we assign any weight, that is a weighted graph. Weight to the edges. Suppose in this picture, we can assume that from A to B, it is like 4. That means if we traverse from A to B, it will cost 4. Unit we don't consider over here. It depends on the scenario, what type of graph we are considering. Basically, graph is used in our real life scenario in case of, this type of problems. Like if we are traversing, if we there are many points we have to traverse, one person have to traverse. In case of deliveries, which path will be the shortest one? A delivery boy is delivering several things to several people, several places. So if he is considering the longest path, it will take a lot of time, right? But if he is considering the shortest path, which will, which he can use to deliver, that will be easier to him and to the customers also. In case of that kind of problems, we can consider this kind of scenario of graph. So I think, I don't think actually it's the scenario only. So there's the scenario when we use graphs. Okay, I hope it's clear. Okay, next one is weighted graph and connected graph is done. Next one is complete graph. See, in a complete graph, what it happens is, if there are any vertices are there, there should be a connection. There should be edges between any two set of vertices. Suppose this one, there are only two vertices, there is an edge. This is a complete graph, or with two vertices and one edge. Okay, this is a 3 vertex graph which is also complete, denoted by K3. In case of complete graph, these are denoted by K. So this is complete. How this is complete? Because they are connected with each other. You take any two vertices, any two vertices you take, that will be connected by an edge. Any two vertices. So similarly, K4, K5, K6, K7, all are connected with each other with any edge. If you take any two vertices among these graphs, they will have one edge between them. So that is a complete graph. Every vertex in a complete graph will have one edge. It is must for a complete graph. Clear? Okay. I'll stop here about the basics. Okay. It will be taught. Some more basics will be taught by PDC ma'am in another class. I'll just directly go to the graph representations. Okay. In graph representations, I hope this all of until now this is clear. Okay, the graph representation, there can be two types of representation: sequential representation, what we can have, list representation, and we can represent with adjacency matrix. See, there is an undirected graph over here, and then we have, I hope this is clear until now. If there is any question, you can just directly ask me in the chat box. Okay, this is an undirected graph, and this is the adjacency matrix. How we are representing this? See, the set of vertices will be, you know, noted in the rows and the columns also. And if there is an edge between these two vertex, it will be, okay, thank you, Sudeshna. It will be denoted 1. And if there is no edge between these two vertex, it will be denoted as 0. See, from A to A, there is no edge, because this is the, this is the one vertex, right? There cannot be edge if there is not self loop. There is a thing called self loop. Let me show you like this. Just wait. Okay. If there is like this thing, like this, if there is anything, this is called the self loop. If there is self loop, that will contain 1, then it will be 1, but it is not containing any self loop, so we cannot consider it as 1. From A to A, there is no edge, that's why it's 0. From A to B, it has edge, so that's why it's 1. From A to C, there's no direct edge. See, we can traverse from A to C via B, but we cannot traverse from A to C directly. That's why it is 0. And from A to D, there is an edge. This is the edge from A to D. That's why it's 1. And from A to E, there's no direct edge. So we are considering it 0. Similarly, from B to A, as this is an undirected graph, we'll consider this edge. We can traverse both way, like A to B and B to A. This one single path will be considered. This path will be considered for both ways. So that's why it is 1. If it would have been an undirected, then it won't be considered. I'll show you in the example also. From B to A, there's an edge, direct edge. Just remember, when you are considering an adjacency matrix, you have to consider the direct edge. Okay, you cannot consider via media. Okay, so this is how the adjacency matrix are drawn. I hope it's clear. If not, please let me know. So this is a, definitions are given, just what I have taught you right now, that is only given over here. Nothing is new. So I'm just directly going to the directed graph. This is a directed graph. See, over here what it is happening, for A to B, it is 1. A to A, it's 0. There's no self loop, that is it's 0. It's clear. For A to B, it's 1. Okay. But for B to A, see, it's 0. Why? Because there's no direct edge. We can go from B to A. We can go with D, via D, but there is no direct edge. That's why it's 0. Okay. So this is how the adjacency matrix of directed and undirected graphs are made. Okay. I hope it's clear. Shall I repeat this one? Whenever there is a direct edge is there. A to B, there is an edge. We can have this edge to traverse A to B, but we cannot use this edge. There is a direction over here. If there is a one way highway, you have seen already. So if there is a one way from Shialda to Newtown, we cannot use that path to return from Newtown to Shialda. We have to take another one if there is one. Okay. It's not clear, Arju? Okay. I'm just repeating. Suppose we are going from Shialda to Newtown. There is a one-way path. Only one way we can traverse. We cannot use the same path to come back. Yeah, I'm repeating. we cannot use the same path to come back. Suppose there is a direction. Here this arrow is denoting the direction. From A to B we are traversing. That's why from A to B it is written 1. Okay. And if from B to A there is no direct edge, we can traverse it through B to D and then to A. But we have to consider in case of adjacency matrix the direct edges. If there is a direct edge, like from B to C there is an edge. B to C there is an edge, but from C to B there is no edge. Okay. That's why from B to C it's 1, but the C to B is 0. Okay. Let's move on, Arju. Okay, it's clear. Fine. Okay, representation of weighted graphs. Now, see, similar kind of things, just in case of 1 and 0, we just have to put the weights. We just have to put the weights. Okay, Anushka, ma'am, can you send the PDF? Oh, of course, I'll send, definitely I'll send. After class, I'll definitely send the PDF. PPT, it's not PDF, I'll definitely send it. Weighted graph, in case of weighted graph, what we have to do? Same thing, just we have to put, instead of 1 and 0, we have to put the weights, path weights. Suppose A to B, the path weight is 4. Okay, this is 4. Please pardon me for my handwriting. It's quite tough to write with the, touchpad. So, from A to B, we are writing 4. See, from B to C, the weight is 2. So, B to C, it's 2. Okay. So, this is how the adjacency matrix are formed. Okay. Let's move on to the next one. This is, which is very important. Adjacency matrix are done. Adjacency list. How it is done? Simple. A to B, if there is A to B, A has only one adjacency neighbor. See, from A, how we can go to, where we can go from A? Only B. See, there is only one arrow, this arrow. Just go to this arrow, follow this arrow. We cannot go from A to D because there is a path from D to A, but there is no direct path from D to A to D. That's why we are considering this one. A to B, that's why it's in the list A to B and there is no any other node. That's why we are containing this pointer as null. Okay. For B, how many neighbors are there? From B, where can we traverse? Just think of it. Where can we go from this node? Just think of that. From B, we can traverse to C. There is an arrow. True. This is the arrow. We can traverse to C, and this is the arrow. We can traverse to D. Anywhere else we cannot traverse. See, B has 2 pointers like C and D, and the last one has no more pointers are there. That's why it's null. This is null because no more neighbors are there in B. Okay. For C, it's E, only E. There's no other direct edge is there. That's why it is containing E and no more pointer are there. That's why it's null. Is it clear? Shall I repeat this one? Just think of where you can go from one vertex. In case of E, suppose in case of E, if we are considering E, where we can go from E? Only see D. Only we can go to D. So, if we are going to D, it is containing D and no more pointers will be there. E has no more neighbors. That's why it is null. It is null. And why this is not null? In case of this, B has 2 neighbors, C and D. So, we are placing C, then we are containing, just think of linked list. We are containing the address of the next node and next node is placed. If there is no more node, the node is null. The last node is null. I am repeating. Okay, I am repeating. If there is A, this is A has only one neighbor. We can go from A to B only. We cannot go from A to D because there is no arrow. See, go with the arrows. So, we are putting B over here and there is no more neighbors with A. That's why we are keeping it null. Think of linked list. Linked list, what we do in linked list? We are keeping one node. In one node, there is a data node and an address node. right? And in the data node we put the data, and in the address node we put the address of the next node. Okay, in case of this adjacency list, what we do, in one neighbor node's address part, we are putting the address of the next neighbor. In case of B, see this one, in case of B, B has two neighbors. See, we can go from B to C and B to D as well. So B has two neighbors. So B has two neighbors. So we are putting from B to C, and then we are putting from C to D. C is containing the address of D only, but there is no more neighbor of B. That's why we are putting this null. This one null. Okay. Now is it clear? I hope it's clear. In case of C, okay, why D after C? It's no B. Why not B to D separate? Can't understand your question, Chirag. Why are you asking? What are you asking? Putting D after C, it doesn't matter. It doesn't really matter if we put D over here. If it is D, if let us suppose it's D. Okay, it's D. Then C will be here. All the neighbor nodes will be here. Okay, it doesn't matter about the order. Don't worry about the order. It's only what it matters is how you how many neighbors do the starting node is having. The start node B is having two neighbors. That's why they are C and D, and we can put D after C as well. Yeah, of course. B to D, then D to C will be a possible. Of course, that is possible. Is it clear, Chirag? The order doesn't matter. Order doesn't matter in case of this. We can put in the order whatever we want. I hope it's clear then. And if we put it separately, if we put two lists for B to D, one is B to D and one is B to C, but that will take extra places, right? Why not we use linked list? That will save our time and space to traverse also. If we are considering one node, we can have one list only and we can traverse the whole list. We can know about all the nodes it is having. So that's the point of using linked list type of data structure in graph to represent graph. Okay. Okay, you're welcome. Okay, so this is a linked representation. Again, for undirected graph, it can be, both ways. Similar for adjacency matrix. See, for A, in case of A, for undirected graph, in case of A, we can traverse from A to B and B to A as well. That's why if A is the neighbor of B, then B is the neighbor of A as well. That's why A is containing B and D, direct edge, and B is containing B is containing A, C and D. Three direct edges. See, 3 pointers. 3 nodes over here. Clear? So, similar thing, you don't have to follow the directions in case of undirected graph. So, this is the linked representation. Okay, in case of weighted graph, what we have to do, there will be 2 pointers. One will contain the data part, the name node of the name, name of the node. Have I gone mad? Okay, name of the node, and then the weight path. Okay, see, from A to B, there's 5. This is 5. 5 is put here. And from B to C, it's 2. 2 has been put here. And B to D, it's 8. 8 has been put here. Then the pointer is null because there are no more neighbors. So this is quite similar. Okay, all of these are similar. The main difference in case of directed graph, we have to follow the arrows. In case of undirected graph, both can traverse in both ways, bidirectional it is. And in case of weighted graphs, we have to put an extra space for the weight node. That will contain 3 parts. One node will contain 3 parts. One is name node, second is weight node, and the third is pointer node, which will contain the address of the next neighbor or null. Clear it is? I hope it's clear. Now we'll start graph traversal algorithm. Okay. Two algorithms are there. I'll directly go to the example so that you can understand it properly. Okay. Then you'll follow this algorithm, you'll get it. Okay. I'll just explain you how it is working. Then it will be easier for you to understand. Okay. First of all, we have to make an adjacency list. This is a graph. This is the graph. Our graph, directed graph it is. You can, all of you can see this. And we have to make an adjacency list. So this adjacency list is containing only the neighbors. We, in case of BFS and DFS, two types of traversing algorithm. Traversing means we have to check each and every vertex. Okay, each and every vertex will be visited. Okay, there is a set of vertex here. There is a set of 7 vertex, and we have to visit each and every vertex with a starting vertex A. Not necessarily it is A for every graph. Depending on the graph, it can be any vertex. Starting vertex can be given in the question also. Just follow my lecture. You can get how to do it. First, the first step is, please take a copy and just take a note. First, you take an adjacency list. Okay. This is the adjacency list for this. See, the neighbors are written. Direct edge, directed edge. Direct edge, directed edge. Consider direct edge, that is A to B, there is a direct edge, and direction you have to follow. Okay. So for A, there are 2 neighbors, B to D. For B, there are 2 neighbors, C and F. For C, there are also 2 neighbors, E and G. See, written here. For G, there are only 1 neighbor, that is E. For E, that is B and F, this one and this one. Okay, this one. So B and F. For F, there is only 1 neighbor, that is A. Direct edge, directed edge. A, and for D, it is only F. So this is our adjacency list. Now what we have to do? We have to take 2 queues. BFS uses queue data structure. We have to take 2 queues. One will contain the nodes which we are processing. Q1 will contain the nodes which we are processing, and Q2 will contain the nodes which have been processed. Okay. Q2 will give us the final output. So there will be 2 queues. Q1 will contain the nodes which we are processing, and Q2 will contain the nodes which we have processed already. So first of all, Q1 will contain the starting node. Okay, A. Q1 is containing A, and Q2 is containing null. No nodes has been processed yet. That's why we are starting from A. Here is the starting point. Okay, starting point can be given in the question also. You have to start from that. We have to check the neighbors. Just make it a note in the, or grab a picture or whatever. You have to just memorize this. Memorize as in when I am explaining, you have to take care of this. Okay, you have to remember whose neighbor is who. So A has 2 neighbors, B and D. What we have to do? We have to process A. Q1 is containing A, and Q2 initially it is null. Okay. So next, Q1 will contain the neighbors of A, B and D. A has the neighbor B and D. A had the neighbor, we have the adjacency list already. So A had the neighbor B and D. So B and D will be added to Q1, and A is processed. Processed means we have visited all the neighbors of the node. Processed means we already have visited all the neighbors through the adjacency list. How can we get the all the neighbors of the node? Through the adjacency list. So Q1 will contain now the neighbors of A, and Q2 will contain A. A will be deleted from Q1 and inserted in Q2. Clear? Next, which node is next? See, B is here. B is here. Again, I am telling, order of the neighbors doesn't matter. If you put BD or DB, same. It's up to you how you want to put it there. Okay. So next node we are processing is B. So we have to first delete B. We are putting B in Q2. B has been processed and B has two neighbors. See, C and F. B has C and F. So we are putting C and F in the Q1. See, C and F has been put in the Q1. Clear? Next node is D. Now we have to process D. What we have to do? In case of D, we have to first put D in Q2, already processed set. Then we have to check about the neighbors of D. Who is the neighbor of D? Only, see, D has only one neighbor F, which is already in Q1, which is already present in Q1. See, F is already in Q1 as it was the neighbor of B. So we don't have to put any new node in Q1. Next node is C. So we have to first delete C. See, C has been inserted. Delete C from Q1 and inserted in Q2, and we have to process it. So C has a neighbor. C has a neighbor E and G. C has two neighbors E and G. So E and G will be added to Q1. See, E and G has been added to Q1. Okay. And now the next in Q1 is F. So F will be added to Q2 and deleted from Q1, and E and G will be remaining. Now F has how many neighbors? F has only A. See, we already have processed A. So we have to check if the neighbor is already in Q1 or in Q2. For case of F, we have already, it has only one neighbor which is A, which has been already processed, which is already in Q2. That means it was in Q1. Any node that is in Q2 cannot be there if it was not in Q1. We are putting in Q1 first, then we are putting in Q2. First it is put, every node is put in Q1, then we are putting in Q2. So that's why A won't be inserted again. A is already visited. We have already visited A. Okay. So that is why F will be directly deleted only. No new node will be inserted. Now E and G. E is the next node. E has how many neighbors? E has, see, here is the adjacency matrix. List. E has B and F. Again, B and F is in Q2. B and F is in Q2. So no need of inserting a new node, already processed. Okay. In case of neighbors which are in Q2 or Q1, we don't have to insert any new node. If all the neighbors of any node already has been processed, already is in Q2, that means they have been processed. So we don't have to visit them once again. So already processed, we don't have to consider them. Next is G. We are putting E in the Q2, already processed node, and G has only E. Again, E is in Q2, so already processed. So we are putting G over here. So this is the final traversal of breadth first search, breadth wise search. Okay, breadth first search, BFS. This is how we done, and this is our final result. Okay, is it clear? I hope it's clear. It's very easy. First, we have to take two Qs. I am just quickly repeating itself. First, we have to take two Qs. First, we have to make an adjacency list from the given graph. Then we have to take two Q. One will contain, I am repeating. One will contain the initial node A or whatever is the initial node, and Q2 will contain null. Q1 will contain the nodes we are visiting or yet to be visited, and Q2 will contain node we have processed already. Okay. Q1. First we have to check the Q1 initial node, check all the neighbors of the initial node, put the initial node in the Q2, already has been processed. Process means we have visited all the nodes of the particular node A. So we have visited B and D. So A is in Q2. Next node is B. So we have to put B in Q2 and traverse the neighbors of B. Though they are C and F. C and F are added to Q1 and B is added to Q2. Next node is D. D will be added to Q2 and neighbors of D will be added to Q1. As the neighbors of D is only F and which is already in Q1, we don't have to add it once more. So we are keeping it like that way. Next is C. For C, there are E and G. So E and G are their neighbors. So C will be added to Q2 and E and G will be added to Q1. In this way, we have to traverse each and every node until the Q1 is null. Q1 is empty. Here Q1 is null. After traversing G, Q1 is null. So when G has been processed, add G to Q2 and make Q1 null. Initially Q2 was null and Q1 has the initial node and Q1 is null at the last position and Q2 has all the nodes that are processed. So this is our final traversing. How we are going? Just follow the order of the Q2, A, B, D, C, F, E, G. This is the final result, final traversal. Okay? This is how you have to do in the exam hall also. Okay, just follow this. I hope it's clear. Now one more traversing algorithm is there, that is depth first search. Just follow the algorithm. If there is any doubt, please feel free to WhatsApp me. I am available on WhatsApp. Don't worry to don't hesitate. Just follow me with this. For depth first search, the same thing is happening with a data structure stack. We use stack instead of queue. Okay, instead of queue we use stack. First we make adjacency list. First we make the adjacency list. Then what we do? Same thing. A has the neighbor B, D. B has the neighbor C and F. C and F. See, B has the neighbor C and F. Similar way we have to make the adjacency list. Now what we have to do is push. We have to push instead of queue. We have to push the starting node into the stack. Initially for BFS we have used 2 queues and in case of DFS we will use only one stack. First we have pushed the initial node H in the stack. H is pushed in the stack. If then the neighbors of the pushed initial node will be pushed after popping the initial node. First we pop the H, pop this node and the neighbors will be pushed. Neighbors of H are here the adjacency list is A. So neighbors are A. So A will be pushed in stack. A will be pushed in stack and H will be popped. First we have to pop because in case of stack always remember the top element will be popped. So if we push A, then the top will be A. So we don't need that kind of situation, right? We have to push A after we pop. First we push the initial node. Just follow clearly. Listen carefully, you will understand. First we have to push H. Then the initial node. Anything can be the initial node given in the question also. First we have to push H. Then we have to pop it when we have checked the list. We have checked the list. It has neighbors. We have contained in a temporary data pointer that it has this neighbors and pop H and push the neighbors in order. Any order. Okay. It has only luckily one neighbor A will be pushed in A stack. So now stack has A, only A. Now what we will do? We will pop A and process the neighbors. A has 2 neighbors. A has B and D, 2 neighbors. So BD will be pushed after A will be popped. Whenever we are checking the adjacency list, then we pop the node top of the stack. Then we will push the adjacency list data, that is the neighbors of the node which we have popped right now. It depends on the graph. See here H is you can start with A as well, but the graph it is settled depth first. So we have to go depth wise, as in the graph is initially this see from H to A it is going. That's why we are starting from H. It is not necessary we have to start from H. The starting node can be given in the question also. Okay, there's no necessary hard and fast rule that we have to follow, that this is a starting node or something else. Okay, so it can be started with A also. We have followed the depth first search. This is like a pyramid, and this graph is like a pyramid, seems like a pyramid. That's why we are going from depth wise from H to A to D to F, whatever. That's why we are considering H over here. It's not necessary you have to also consider H over here. You can consider A also. Follow the process just. First we have to push the starting node, then we have to check the adjacency list to find out the neighbors, then we have to put into the stack, pop the initial node, and then the push the neighbor nodes, then follow the same process again and again until the stack is empty. Okay, all the neighbors are processed. So H has been pushed, processed, H's neighbors are processed. We have checked the list, H popped, A has been pushed. Next, neighbors of A, B and D are checked in the adjacency list. So A has been popped, printed. That is also already printed as output. First printed H, then printed A, and B and D will be pushed in the stack. Next node is, suppose B and D is pushed. So D is the top. So neighbor of D we will check, that is F. Neighbor of D is F. We'll check the adjacency list. Then what we'll do? Pop D, that will print D. So first we have printed H, then we have printed A, then we are printing D and pushing F. Okay, pushing F then as a neighbor of D. Then what is the top of the stack? F is the top of stack. So if F is the top of stack, what we have to do is check the neighbors of F. Check the neighbors of F. F has only one neighbor, that is A. But A is already printed, that is popped. So if any node has been already printed and it is coming with the neighbor node, we don't have to consider it like the BFS only. We have processed already A, so that we won't consider. Okay. So A won't be considered. Print F. Now stack is containing only B. Only B is contained. So neighbor of B will be checked and B will be printed. Neighbor of B is C. Only C. So B will be printed and C will be pushed in the stack, and now C will be processed. We will check the adjacency list and C, we can see that E and G are the neighbors of C. So C will be printed and then E and G will be pushed in the stack. Now what is the top of the stack? G. So we will process G. So we can see that G has only two neighbors, E and H. Okay, among which E is already in the stack and H we have already processed. H is printed in the first place. So in case of G, we cannot consider once more H, and E is already in the stack, so G will be printed. So first we have printed H, then A, then D, then F, then B, then C, and now G will be printed. Now stack is containing only one node, which is E. E has no new neighbor which isn't processed yet, which isn't traversed yet, visited yet. Whatever you want to say, visited, traverse, whatever. So E will be printed. So the printing sequence is the final output of our DFS, depth first search. This is our final output. So that is the main purpose of traversing the graphs in two ways. Depending on the graph type, we can traverse in both ways. Breadth first search, breadth wise, we will just follow the child parent child node kind of thing. Like in depth first search, what we were doing, we are just going through like this. How many neighbors are there? Just process all of them first, all of them. A has 2 neighbors, process all of them first. But in case of depth first search, we are not processing every neighbor at once. We can process one neighbor at a time, and the second neighbor can be processed later also. So first what we have, I am repeating this one time once more so that it will be clear. First one is initial node will be pushed in the stack and the neighboring nodes will be visited in the adjacency list. H has A, only one neighbor. So print H and push A in the stack. Next, top of the stack is A. We will check in the adjacency list how many neighbors are there. 2 neighbors, B and D. So print will be A, that will be popped out from the stack, and in stack we will push B and D. Now the next top of the stack is D. We will check D, neighbor of D, that are only F. So we will push F and print D. D is already popped out. Next, top of the stack is F. See, here 2 neighbors of A, B and D are inserted in the stack once at a time along with that, but we are not processing it sequentially. We are processing D, then F has came as the top of the stack. This is how breadth first search and depth first search is different. Okay, so we are considering F, then F will be processed. F has no new neighbor.